Good morning, good afternoon, and good evening, wherever you are. Thank you for joining. At CIQ, we're focused on powering the next generation of software infrastructure, leveraging the capabilities of cloud, hyperscale, and HPC. From research to the enterprise, our customers rely on us for the ultimate Rocky Linux, Werewolf, and Apptainer support escalation. We provide deep development capabilities and solutions, all delivered in the collaborative spirit of open source.
Well, hey everyone, welcome to another CIQ webinar. Thanks for joining us. Rose, I was all excited to, first of all, I'm joined by my partner in crime, Rose Stein here, and we are excited to be taking over the kingdom. I guess Zane's on a plane, so he couldn't make it this round, and I'm sitting in for him, and we'll see how it goes. I don't know what they're thinking, Rose.
I imagine that he's watching though, and we'll probably get a couple of like side messages of like, what are you guys talking about? What are you doing?
Exactly. Well, we'll see. We're looking forward to having him back next week. But this week, what are we talking about? What are we looking to discuss?
You know, this is actually interesting, and I am really excited to hear different people's perspective on this. So it's unlocking the power of turnkey HPC interconnects to accelerate workloads.
Okay. Well, please tell me we have some smart people to talk about this, because I am very new to this. This will be new stuff for me. I know what an interconnect is, but it's been 20 years since I've even thought about that in an HPC perspective. So who do we have on? Let's unleash the. We got Gary. Fantastic.
In the house. Awesome. Hey,
welcome, Gary.
Hi.
Nice to see you.
Oh, look at that. I knew we had other people in the wings. All right, well, let's go ahead and intro. Gary, we'll go ahead and start it with you.
My name is Gary John. I run the institutional high-performance computing for Lawrence Berkeley Laboratory, and I also manage the UC Berkeley institutional high-performance computing program also.
Awesome. Jonathan.
Yeah, my name is Jonathan Anderson. I'm a solutions architect here with CIQ, and I have a background in academic high-performance computing.
All right. Alan?
Yeah, Alan Sill, and like Gary, I wear two hats. I run the High Performance Computing Center here at Texas Tech University, and I also am one of several co-directors of a multi-university industry university cooperative research center in cloud and autonomic computing with funding from the National Science Foundation.
All right. Dave.
Yeah, hi, I'm David DeBonis. I'm a computer scientist over here at CIQ with a background in HPC embedded systems, mostly focused on system software.
All right. And we got a new face here, Matthew.
Hi, I'm Matthew Dosange, a senior member of technical staff at Sandia National Laboratories. I work on HPC middleware and research around that. Particularly MPI and OpenSHMEM and SmartNICs.
Awesome. Well, thank you guys for joining us. I really appreciate it. Hopefully this you'll be able to fill us in on all sorts of questions that we've got here about HPC interconnects.
Yeah.
So Rose, you got the first question?
Yeah, you got to break it down for me though. And like maybe Matthew, we'll start with you. So you are a new face. Hi, it's nice to meet you. Thanks for being here. Can you break down like what are interconnects, and then why is this important to the HPC system?
So interconnects are kind of our form of networking. In a sense, we run on trusted systems with very low latency needs for networks for scientific applications, so that we can run hundreds of iterations across thousands of nodes a second. And so having the overhead of Ethernet and that network stack doesn't really work for our use case. So there's been a long history in different companies making interconnects ranging from, Tray to the InfiniBand stack, and now we have kind of a new generation coming out now. But the idea of having a low latency networking solution for a trusted user base is kind of the big thing.
Awesome. I appreciate that. Thank you. So what are some of the different types of interconnects? Gary, you want to jump in there?
Boy, there's the standard Ethernet interconnect that Matthew was talking about that connects, everybody uses to connect all the compute nodes. But usually when we refer to interconnect or a fabric for a high performance computing system, then we're looking for something that sometimes could be more performant than an Ethernet connection. So the one that most people have converged on these days is InfiniBand, and there's different generations of that. But the current generation of that that is currently on the market is 400 gigabits per second. So that is quite a bit faster than most people would deploy with Ethernet. And so in addition to the higher performance, you would also get low latency. So it'd be very low latency for tightly coupled jobs where there's communication between the compute nodes.
And Gary, what are those? What are the actual physical connections, or is that all optical?
It can be if they're within the rack, you can use passive copper cables, and they use a QSFP connection. And if you go out of the rack, then you're going to be required to use optical connections.
Okay, so you're going for
InfiniBand these days can go quite a distance. You can go probably to other areas within your campus with just optics.
Oh, cool.
At some sacrifice of latency. That's correct. Yes.
Yeah.
So I think we have to understand that the fundamental purpose of interconnects is to provide parallelism. The recent talk by Torsten Höppler of at the HPC Advisory Council, I'll see if I can find a link, talked about the three types of parallelism: data parallelism, pipeline parallelism, and operator parallelism. And that's all pretty abstract, but the idea of a high-speed interconnect is to allow more than one node to be used at once, really. It's kind of a simple fundamental concept. We have to understand that there have been a lot of complications lately. And certainly the field has always explored alternatives. We've seen people try to produce switchless fabrics, all optical interconnects. Rockport is popular in that area, working in that area. There's always been alternative technologies. Cray has its slingshot, which is derived from Ethernet. Omnipath is still on path to coming back. Cornelis has been pursuing, but I think Gary's right that InfiniBand is what people are familiar with in the sort of generic plain vanilla HPC cluster. Other complications have to do with ways that we're putting accelerators into the mix. So GPUs often are deployed in sets with dedicated interconnects that bypass the conventional ones. And also we have to unveil a hidden secret, which is that most clusters use the interconnect fabric not just to allow computations to take place across multiple nodes, but to get high-speed access to storage. So there's a kind of a hidden overloading of the function there that sometimes trips us up a little bit.
Mm-hmm.
I wanted to just toss in this just for a comparison, but when interconnects, when I used to look at the top 500 list, one of the things that was interesting is that you could look at the different rankings of the clusters, and it would approximately, if you compare an InfiniBand cluster to an Ethernet cluster, it took approximately twice the compute power of the Ethernet cluster to come up with the same score on the HPL LinPack as an InfiniBand cluster, or at that time even a MirrorNet cluster because of the latency. And just the HPL is, it's a depends on the parallelism that is supported by the low latency that Alan was mentioning.
Yeah, Alan, you mentioned Torsten, and I think he said during SC this year, Torsten, of course, is going to say this, but networks are the future of HPC, and it is because they're moving so much data around, and usually a lot of jobs, I would say, are mostly communication bound. Some of the aspects of like RDMA, other sorts of technologies, the separate channels, those help to make it more efficient at the fabric layer and make it more parallelizable.
So there's another thing, guys, that as we're talking about this topic, another word that is kind of fun, because every time I ask somebody, they have a different answer, but it's talking about turnkey HPC, right? So unlocking the power of turnkey HPC interconnects to accelerate workloads. What does that mean to you?
I have to confess that left me a bit baffled. I have never found a turnkey interconnect. They are highly cantankerous herds of thoroughbreds, if you want to make a very stretched analogy.
Can we say CIQ is your turnkey?
Well, so you're welcome to come over. We have several interconnect problems. I'd be happy to point you towards. But it's a dark art. Well, maybe that's too extreme. It's an art. And the interplay between driver versions for the fabrics, different generations of fabrics, fabric interfaces on the same card, the care and feeding of the cables themselves, and people don't realize that there's firmware in those cables. There's a little computer in each end of one. So it's not just stringing cables together.
Yeah, scalability.
We used to say that. Oh, sorry.
Go ahead. No, go ahead, Gary.
I was just going to make a comment. We used to say that every cluster is serial number 1.
Yeah, I think that's what I was going to say. It's very dependent on your system and the needs of your system and the workloads that come through it. So it is customized, just like any system would be customized to, let's say, a video gamer that plays video games on their high performance system that is their workstation. Who knows? So it is. You have to worry about scalability, fault tolerance, a number of areas that will be very particular to an installation.
Yeah, cost is a big factor. So I'm at a university. We build, modest scale clusters, and I'm willing to make some controversial statements. I actually never understood people who build clusters at our scale or even a little larger that don't max out the bandwidth on their fabrics these days to the limit of what they can afford. I'll give you an example that 2 years ago, we put in the first university-based AMD ROM system in the country, modeled after one that had just been built, the Hawk supercomputer in Germany. And shortly thereafter, a lot of these started to pop up. And I was mystified by people putting in HDR 100 connects to dual 64-core nodes, taking giant leaps backwards in bandwidths per core. Anyway, I could go on like this for some time, but Matthew hasn't jumped in yet. I wanted to see if
I was gonna say that the one thing that also is difficult about turnkey in a sense is that these networks have been progressively getting more and more complex, and that's one of the things that we struggle with is like, you look at NVIDIA's Mellanox or the new Cray Slingshot, and they're providing all this additional technology on the NICs, and we're still trying to figure out from a software perspective how to utilize this. And it makes it, as you add more and more components, the harder it is to have a true turnkey solution.
Yeah, and tuning those components is an art in itself, right? And not just the sizing and deciding I'm going to have these particular pieces of hardware and this topology. It's even just getting them, performance tuned.
I think any exercise in creating a turnkey HPC solution, and let alone just specifically the network, is going to be an exercise in tuning something for a specific use case. And there's one set of selection that's selecting like the components that are usable, like DPUs and things like that, that might be useful in your application or in your suite of applications. But once you have a software stack and hardware stack that works together, and we can just set aside the firmware has bugs and the drivers have bugs and all of this needs to be maintained and kept up to date. Once you have all that, you still have questions like Alan mentioned, the aspect of cost. Like maybe one deployment doesn't need dual 64-core CPUs and the bandwidth to feed that. And understanding what an application can actually take advantage of, and then how broad your network needs to be in order to fit that. We'll talk about topologies a little bit, I think, later. But not everyone needs a full bisection bandwidth non-blocking fabric across all of their nodes, depending on how far their application could scale across multiple nodes and multiple cores.
Yeah.
Can't hear you, Alan.
Oh, yeah, Alan, you're on mute or something.
Hello, can you hear me?
Yes.
Yes. So I hear that statement a lot, and I think it's objectively true at a rational level, but it's also, I'm willing to argue, not true at all for medium and small scale clusters.
Yeah.
If you're going to go subdividing the bandwidth of your cluster up into trees and islands, they're going to introduce scheduling complications that are especially severe in modest scale deployments. You're going to spend your time waiting for large jobs to schedule to fit into whatever islands of good connectivity you have. And, the dual 64 core is, old, right? It's, 96 now, and dual, the dual nodes are hard to build. The small one, half U nodes, I don't think we're going to see any dual nodes for a while. There will be full U units, but nonetheless, you're not going to have one HDR 400, or you can put one HDR 400 interconnect into that, and you will just have the bandwidth that I have out of my dual 64 core HDR 200s, right? It's an arms race that's taking place in your backplane. And in the earlier discussion, I forgot to mention that there are other things competing for that backplane bandwidth. Things like hyperconverged system, what do you call it? Composable computing, right? The PCIe networks and everything. The weakness I often point out is it's yet another fabric, but those things have to talk to your motherboards and use up bandwidth on them too. So it's you have to watch the bandwidth per core ratio, the fabric NUMA assignments, and a bunch of things. Now, as to the point you made about topology, Jonathan, I think you're right, but I've been building full bisection bandwidth modest scale clusters for a long time, and I've never regretted it. When you get big, and I put a link in our internal chat that maybe someone can drop into the external chat. The talk that Torsten gave talks about what I like about him is he always makes these declarative statements that you're left to puzzle out. The future is sparsified, he says, and then he has lots of slides about how you really need all the bandwidth you can get locally. So I'm not sure what it all means, but I will say that the topic you're raising, that of topology, is very important for large scale clusters. But I'm willing to advocate that all medium and small scale clusters, anything less than a few hundred nodes, these days, given the core densities, you should spend money to get good connectivity. So yeah, Gary, you raised the question of Ethernet topology, and Ethernet's, of course, the basis of Cray fabrics, and the Cray fabrics have, I think, caught up in terms of bandwidth. Do you have Cray deployments that you can look at?
Not that I manage though, but NERSC at our site has a slingshot. Yeah, and you're right. I was going to also add to what you were saying. We're just starting to see the emergence of these multi GPU nodes, and for the people who are training large models, then the communications is a bottleneck, and so even a single 400 gigabit connection sounds a little light for an 8-way GPU system, as if you're doing training.
Yeah, that kind of brings what Alan said earlier too, is your local node and its interconnects, its NUMA nodes, all of the things that are separate kind of memory domains, but shared bus for at least the PCI bus. Those are the trade-offs and the trading points when you're on a small system, and probably the focal points of you really want to maximize your node, I think, more than even your interconnectivity. I'm not an expert on that, but it feels like you want to do as much locally as possible to avoid that data movement as much as possible.
Yeah, so we can look, at why dual socket nodes became so popular in HPC. It's almost the default. It's certainly not by any means universal, but it was partly because of the cost of the interconnect. They were trying to get the most bang for the buck building clusters out of nodes, at that time they thought they could just put more sockets to share the same interconnect and the rest of the infrastructure. Now I think it's time to question that. When you have 128 cores in a socket, maybe you need a dedicated card per socket. Maybe we should be looking for other ways to optimize cost. And that leads right back into Jonathan's question of topology.
I think that's a cue, Jonathan.
Yeah, so how do you choose like an optimal topology? Like, I mean, are there steps you take to kind of dissect the work you're working on, or how does that work?
So again, I have to refer to Torsten's talk because I was just really impressed with it. It was only a few days ago that it came out, and there's certainly been other summaries in the past, but it talks about these three types of parallelism: data, pipeline, and operator. And it also talks about the topic that Gary raised, which is the interconnects of accelerators. And it depends on your scale and what you're trying to do. He introduces, at least for me, something new that probably has been around a while, something called a Hamming mesh, which has, he says, many configurations. But there are already alternatives to fat trees. There's, a popular one is butterfly, and then there's various types of torus interconnects. To me, again, they make the most sense when you have a big enough cluster to make the difference. But for small things like a few dozen GPUs, you may already benefit. For example, if you've just got a few, you can use NVIDIA's NVLink and get faster interconnects between just a few. So the question comes, how do you connect a few dozen to a few hundred? And I don't have enough experience with GPUs to answer that question. For CPUs, I think any less than a few hundred, you should just do a fat tree.
Yeah, it's interesting because one of the Matt's in the center that I used to be a part of as well, and his father, I think it was his father that coined the phrase co-design. The whole center's concept, and it was the Computer Science Research Institute at the time, or computational science, and the whole reason for it was to get both the application developers, the middleware developers, the people that were doing the linear algebra packages, and the people that were doing the system software, and the people that were doing some of the underlying hardware or investigating hardware, to understand their neighbors really well. And that was the way that for at least supercomputers. That's the way that you get a highly tuned system that can get onto the top 500. For a small system, yeah, maybe there is a more blanket turnkey kind of solution.
Yes, so David, you raised an interesting point in passing here, which is the role of software. We've managed to gloss over it up to now because I think largely because of the work done by a number of people to develop the standards that we rely on now, so that we can ignore the complications, so that we have, InfiniBand, verbs, and MPI. That's a very complex topic that usually does and historically has depended, been in different states for different types of interconnects. Let's just say it that way. And I think the community has done a great job of coming together and trying to hide that level of complexity from the average user. It's still there, but I think we don't spend a lot of our time thinking about the details of getting the hardware to communicate because of the work of the committees.
Can you guys actually expand a little bit more on what you mean by price? Is it like literally the price of the hardware, or is like, Gary, you mentioned energy. You said it takes like a double the amount of energy. So when we're talking about how much things cost, what are we considering?
I was saying it was like that it took twice as much compute on an Ethernet cluster as compared to an InfiniBand cluster to achieve the same amount, achieve the same result on the LinPack test. But if you're talking about price, I guess usually when you're designing clusters, there's kind of like the compute budget, there's a storage budget, and then there's an interconnect budget. And usually the interconnect on the more parallel systems, the more parallelism that you're going to do on the system, the higher percentage of the budget should go to the interconnect. And so it can go anywhere from a interconnect with a blocking factor, like say 2-to-1, 3-to-1, even 4-to-1, to what Alan called a full section bisection bandwidth, where essentially all the nodes on one half of the cluster could talk to all the nodes on the other half of the cluster without any kind of blocking.
Yes.
So that's where the cost comes in. Yeah.
It's also probably worth noting that, like, when we're talking about networking and InfiniBand and stuff like that, the cables themselves even are more expensive than what you'd think of from a more traditional Ethernet network, right? Where, the cost is for the network and the compute resources is, especially for large systems, which is where I spend my time doing research, can be astronomical in a sense. And then you have to worry about power costs and everything like that just to operate the machine.
Yeah, correct. So let's go back to a point that Gary raised. Typically you'll make connections within a rack on copper, and then maybe between racks, or certainly longer distances with optical fiber. Copper cable could cost a few $100. Optical cable can cost $1,200, depending on what it is. So when I say a modestly sized cluster is easier to build with a full fat tree, full non-blocking, folded cloth network, if you want to be a computer scientist, that's one of the reasons. The cables just cost you less, and there are fewer switches involved. The bigger the systems, the more. There's roughly basically identically a 2-to-1 ratio, but roughly when you fold in storage between the leaf switches and the core switches, the number of switches grows with the cluster. The cost of switches is non-trivial. It can be tens of thousands of dollars. And back to another point that Gary raised, the Ethernet sort of pre-slingshot Ethernet, classic Ethernet, can be used to build clusters. And the reason that people were willing to put up with lower performance, more chattiness, more latency, and so forth in Ethernet was that the switches and cables are so much cheaper. So that's why, especially a lot of the early Beowulf clusters were built on Ethernet.
So one of the things too on cost, I remember when I first started in the group over at Sandia, we were really thinking about fault tolerance and power. It was a really big thing. Resilience from a fault was important because we were seeing that systems were failing because the chip counts were getting up there to the point where we were scaling, by the thousands of flops each whatever cycle. I don't want to get into the whole when are we going to get exascale thing, but that they were going through. It was always pushed out a couple of years. But it did seem like the fault rate of the actual devices was going to be so substantial that the system would never make progress because it would always have to fall back on a checkpoint to get back up to speed and then go forward. So when you have more chips, when you have more devices, that you'll have more failures. And so that's something to keep in mind too, the maintenance cost and the uptime or downtime cost of your system, no matter what the size, really.
Yeah, as you add nodes, your mean time to failure just shrinks drastically. And when you start looking at positioning of your cluster, right, like we're at 6,000 feet here, you go up to someplace in the mountains like Los Alamos, it becomes actually significant compared to having something like closer to Berkeley, which is closer to sea level.
Yeah, it's interesting because cosmic rays, believe it or not, it really is a thing. Matter of fact, one of Matt's colleagues did his dissertation on just that. I think on a study with comparison between Los Alamos and might have been some Sandia stuff, but I can't recall.
So how does that impact it? That's really curious. Is that just adding more errors, or what is it? How are cosmic rays impacting?
Bit flips.
Bit flips. Yep.
Wow.
Yeah,
Oh.
and there is, of course, error correction and retries, but overall MPI is still remarkably fragile. So Jeffrey Fox did a lot of work on looking at the comparisons between, for example, MapReduce and classic MPI, and looking for ways that the MPI standards could be made more robust and resilient to failure. But pretty much if you lose a node during a calculation, you lose the whole calculation, no matter how many nodes are in it. Still, even in spite of this kind of work, I think we need more such work as we build exascale systems with very large number of nodes. The points that David raises become very important, and we're still here. Though they've done a lot to tamp it down, we still hear a lot about the reliability of the largest of the exascale deployments.
I will just hop in here for a second and say that this has been an ongoing topic in the MPI forum. We're finally at a point where errors aren't necessarily fatal, which we got to maybe 2 years ago or something like that. But like even an out of memory error would just kill your MPI application, which seems a little insane in retrospect. But
yeah, I believe Matt is on the MPI committee, right?
I am the Sandia representative for the MPI forum and in the Open MPI developers community.
And I want to plug your conference.
Oh, yeah.
So he's also co-chair with another former colleague and friend for Hot Interconnects this year, which is the IEEE standard. I think it's the 29th year. And so
I believe so. So I'm the vice chair. The chair is Taylor Groves out at Lawrence Berkeley National Labs,
yep.
Working in NERSC, and yeah, if anyone has papers that they want to send over, or we run a free virtual conference, so it is there's a lot of good talks and there's no cost to attend.
Cool.
Nice. Thank you.
Yeah, so I'll just say on behalf of the community, thank you, because this is incredibly important work and it does require detailed understanding.
Yeah. So I have a question, guys, and I would like to hear from every single one of you if you don't mind. And, definitely it's going to, change based on what the use case is. But say, for example, you're going to build a cluster, let's say for a university, like Allen's University. Like, what would be like the perfect system? Like, how big would it be? What interconnects would you use? Start with.
I'll go first because I have no idea how to address that. Other than to say, my focus has always been on using the power that you have available, and performance of a large cluster that is not utilizing its power cap is kind of wasting money. It's throwing money on the floor. So my research that I did was in focusing on power efficiency. So how well did an application or a system use its power envelope? And how well could you reconfigure those into a lower power state or into a smaller power window, or a longer execution time to help load balance a system? So you can do that on any system, and you can make any system somewhat performant. I guess that's a subjective term, but I think that if we start to look at systems instead of how much money can we spend and how much fabric can we have and how much, the new fancy stuff that we have out there, how complex can we make it? If we start to look at our workloads and how can we tune them better and how can we really get that understanding of how well an application or a workload is utilizing the compartment it's running in. That would be my approach, because I don't know how to answer it otherwise.
So Rose, let me back up a little from your question and define the terms, right? When you say university, let's just sort of describe what that environment is. Gary's familiar with this as well. You guys do have a lot of customers in this area. So university workloads are typically highly mixed in terms of they don't have just one dominant kind of application, or if they do, it's it's maybe due to special funding circumstances of a group. But you have a mix of workloads from very small core counts up to very large. And if you ask yourself, I should have prepared a graph. I have a graph where I show this. The distribution of jobs versus core count is highly peaked at the low end of small core count jobs. But if you ask yourself at any given time, how many of my cores are occupied by small core count jobs versus large core count jobs, after the schedule has done its work of balancing things out, you find that it's sort of the 10 to 100 and 100 to 1,000 bins that get the most populated. So yes, there are a lot of very small core count jobs, but each larger core count job takes more cores. So if you're asking yourself how many of my cores are taken up, it turns out that the medium scale jobs, and I think a lot of these environments will dominate. So then you have to ask yourself, what can I do in designing my fabric, storage, CPU, to get the most productivity out? That's where the questions I raised earlier come into play. So I find, with we have about 750 nodes here, and with a cluster on that scale, having non-blocking topologies just helps the scheduler do its job more efficiently, and stuffing all the little jobs in to the corners where it can between the big jobs. That's not the only way to do it. Look at bridges. It's a couple thousand nodes, I think. They have a oversubscribed fabric with non-blocking in, I think it's not quite per rack, maybe it's a couple racks. Expanse, they do non-blocking per rack, and then oversubscribed between racks. That means your scheduler has to fit those jobs, those bigger jobs, into a rack, right? So now I say rack, but the densities are such that you really be talking about a switch pretty soon. And that's say you have a 40 port switch with 20 ports going to worker nodes and 20 to upstream. Then or maybe even oversubscribed. Then 20 nodes at 256 cores a node is a pretty big job. So these are the kinds of things that you have to factor in. And I think if you phrase it that way in terms of workload, then you can get out of the area of just talking about a university and look at other similar workloads. This might apply to a small bioinformatics firm or to a number of different settings. When you get to the really large scale topologies, that's where the fancy fireworks come out, right?
Cool.
So it sounds like really what's driving this is really understanding your workloads, understanding what you're really trying to solve, not coming out and saying, how much can I buy? Where can I, how can I build this out? It really is kind of reverse engineering it.
Mm-hmm.
Okay, interesting.
Yeah, and especially with the rise of so much compute power in a GPU and the need for data movement, I think that changes the whole equation. And I think Alan was mentioning that earlier. It's a really important aspect. You have to understand your community and your workloads. And what's the future of the hardware that is coming out next? Because some of these supercomputers, what they do is they do a first initial install, and then they plan out within a number of years, a couple of years or so, an upgrade, so that they don't just do that upfront cost every single time. They have a more longer term path, so that they can get reuse out of them. Knowing what hardware is going to do for the next generation is an important aspect of understanding the system that you're building today and the longevity of that system for future.
I think the one thing that I can add here is that it also really depends on your user base. I was running a panel at XMPI last year, and it was on the use of how are we going to use MPI from GPUs. And we had a very impassioned member of the audience saying, why does this matter? In industry, when we're using HPC, we only program for the CPU because that's what's most cost effective. It takes too much developer time for a small company to port everything to the GPU and do all that other stuff. And that there's a cost balance here of like, how much time am I going to spend writing my code versus how much money am I going to spend on my cluster, like on 4 hours or whatever. And so that for a university, it's really, you want to tailor it to the your expected workloads, and if they need something more than that, there's resources like NERST and TAC that they can get at, or that your users can get allocations on.
Yeah, that's a good point.
We've also been talking about this just in terms of on-premises clusters, but the same considerations play out in the cloud. And the thing that distinguishes them is that, of course, the cloud tries to make its money by selling on demand. And fundamentally, that means that they have to deploy at a scale that's sometimes much larger, but still be able to partition it up for individual workloads. So there's recently been a paper pointed out by Glenn Lockwood, which talks about the InfiniBand structure of the RDMA structure of Azure storage, for example. And it's really a tour de force of doing exactly the things you need to do to have a very large scale fabric deployment but it still allows you to do things like take care of security considerations for keeping an enclave of that available only to that user. I'll see if I can find a link to that.
So guys, how is it measured? Like, how do you measure the performance of your HPC interconnect?
And actually, I'd love to add on to that if we could, because Alan, you were talking about how there are HPC systems that are connected differently, right? In rack, we're doing at this speed. So I'm always curious, like how would you know where, or how would you figure out, along with that, how do you monitor it? How would you know where your bottleneck is? That's kind of for everybody.
So we have a lot of different ways of looking at this that I'm aware of, at least. You know, there's link level benchmarks. I know NERST has collaborated on these large scale kind of noisy networks to identify bottlenecks. What we focus on at Sandia is proxy applications, which are a small application that does something that looks like science and communicates like science and uses the RAM like science, but is easier to understand and doesn't have the testy like core function or performance.
Yeah. Matter of fact, yeah. So the Mantivo mini apps are very much focused towards different aspects of computing, different computing workloads. So certain workloads could be compute bound, memory bound, communication bound. They could be doing a lot of exchanges, point to point. You know, all of the different sorts of ways that you would behaviors. It's almost like they're different behaviors of scientific codes condensed down into a small kernel so that you can get these sorts of benchmarks. And some of the work when I was over at Sandia, I did some multi-generational studies, and they have a beautiful set of test beds there, a number of clusters of different, some are heterogeneous and some of them are homogeneous. They're outfitted with some of the more interesting newer generation stuff that's coming out. And we're able to see, at least to a small scale, we'll do a scaling study still, to a small scale, you know, 4, 32, 96 nodes, how an application or one of these mini apps, the kernels, perform as you start to scale. And usually you can see how an application is going to scale, you know, just by a few different, you know, doubling your size a few times.
Yeah, so with some caveats that many people don't handle the statistics of such benchmarking properly, and that's another whole webinar we could do. But the standard thing to do is to study your scaling. And in practical terms, let me point out, if you're going to ask for allocation on a national scale supercomputer, you're going to need to demonstrate that your application is able to scale. Unfortunately, I'm a little constrained on what we can say. We've actually been doing some work within my center with one of the member companies on improving the state of the art for benchmarking of MPI code. Let me just go back to what I started with. It's easy to fool yourself with statistics when you're benchmarking. You need to be careful, more careful than most people are when they're doing these scaling studies. Ultimately, what the scientist cares about is how many units of X workload they can get through. But even simple tools like total view or debuggers can help you look at how you're using your memory, how you're using I/O. One of the things we have published from my center and we've talked about in previous webinars is that we have open source tools at github.com/nsfcac that you can use on pretty much any modern system that supports Redfish to gather out of band statistics on things like memory power, CPU power, and we're working to fold in these bandwidth statistics so that you can do kind of touchless overview benchmarking of your cluster. How where is it spending time and effort without having instrument code.
Yeah, I think Redfish actually was utilized the Power API, which was a Sandia product that I worked on when I was there. And yeah, it is very important to get those out of band information and not interfere with the workload, or else wait, you're perturbing the system. But it goes back to cost, like you were saying earlier, Rose, or asking about cost. It isn't really dollar cost, it's science, like Alan had alluded to. It's the cost in science. How much science can I get done on this system? And how do I get it done very efficiently so I can get more science done? It's kind of as simple as that, I think.
So Gary, how often do you get researchers coming to you and saying, can you speed up my code, versus just, I can't get this to run?
It does happen. It does happen. Usually most of the issues are these days that I can recall, like say in the last couple of months, have been IO related. And so it hasn't been with the interconnect, it's more with the IO. But they do.
So I guess we're getting towards the end. One of the things that I was curious about is because I talked to a bunch of customers who are kind of looking for direction, and I was curious what is the state of the art right now if you were to recommend an interconnect. And I know there's obviously depends on the workloads, but what's kind of the state of the art? And Alan, I know you may not be able to say and dive into what you're talking about, but if we were to go to off the shelf, what would that be?
Listen, I think it's more competitive than people realize. Like Gary said, most people's starting point is InfiniBand. But let's face it, InfiniBand is expensive and touchy. I've got both an InfiniBand and an OmniPath deployment, and the OmniPath never gives me any trouble. The InfiniBand, I have to be careful with every version update, and there seem to be lots of ways that small communication errors can interrupt performance. I'd mentioned the switchless fabrics, the Rockport style ones. You just put a different PCIe card. You don't have either InfiniBand or OmniPath, but it is limited in the number of nodes you can connect. So the great advantage of that is it's very little latency. I mean, essentially no latency. Well, not none, but it's sort of PCIe backplane latency at that point. Then we also have the PCI interconnects, the composable computing fabrics. So you can buy a box of GPUs and shove them in, and depending on your workload, again, if you need those GPUs to communicate or not communicate, you could save a lot of money if you don't want to spend a lot of money on interconnects by just having a box of GPUs, running them separately. So all of the above.
Okay.
But I think most people do start, as Gary said, looking at InfiniBand fabrics, and that's a good place to get your feet wet.
Yeah, I think what was it? With Mellanox now being owned by NVIDIA, and then OmniPath is spun out of Intel, there's kind of a hardware dependency that is a little bit baked in to some of these.
I would say affinity.
Yeah.
Yeah, I worried the same sort of thing when Xilinx and Altera left the marketplace and got consumed by AMD and Intel. Same sort of thing. They're smart. They know that's going to be the optimization path, and they also know that the ecosystem and the people that are out there that can do those things are very limited. Even though Xilinx was trying to create the tools for an ecosystem of design engineers to make their own fabrics. So in a way, you're steered. You're always a slave to the industry and the movement in the industry. So your decisions of what you get could have to do with who owns what, which is a sad reality, I guess.
Yeah, so we're running out of things that NVIDIA hasn't bought, right?
Right.
Well, going down that path, do we see GPUs as kind of being like where this is all heading? I mean, or is there still a need for CPU-based compute, just for pricing or cost?
I think it depends on the workload, and
Okay.
and yes, we definitely do see a need for that with the amount of small compute and large data movement that you see in some of the machine learning codes and training.
Well, and it also depends on your users, right? I alluded to this earlier. We have, a bunch of people working on GPU codes, but there's a lot of people that don't want to deal with that.
Mm-hmm.
And don't want to deal with the added complexity to their science of having both a CPU code to manage everything and then moving stuff over to the GPU and moving it back, doing your communication. We're trying to figure out how to do MPI from the GPU, but that's very in its early stages and has not been standardized. And we're working on that in the MPI forum, but it's not a reality yet.
Yeah, I think it's a little informed by the topologies of the big clusters too, right? We've seen, let's see, Frontier is 4 GPUs per CPU, if I recall correctly. Then I think the new AMD CPU plus GPU systems are just being deployed where you have essentially, all on a socket, or all within a small portion of the backplane. So my controversial take that I can never get hardware vendors to agree to is that when they build a national scale, really big system, they should sell little units of that system to a bunch of universities, just identical, because then we can get the most out of the software development.
Yeah.
But I can never get any of the hardware vendors to agree to do that because they lose their shirts on these big systems.
Yeah.
Well, we are coming up on the top of the hour. Any final thoughts from anybody?
Well, I want to thank Matt for doing this at the last minute. I just called him an hour before this to see if he can make it. I'm glad he could. Matt's a good friend of mine here in Albuquerque, and we, it was good to see him.
Absolutely.
Thanks for having me.
Sure.
Yeah, I'd love to have you again. This is great.
Yeah, thanks, Matt.
Any other final thoughts? Everybody else good? We talked it out?
Talked it out. Well, you guys make sure that you like and subscribe. We're here every single week, same time, same place, same channel. We will be here. If you guys also have suggestions on topics for webinars, things that you want to dive into, please leave those in the comments. We want to read them and we want to serve our community the best that we can. So thank you everyone on the panel for being here. Thank you for watching. You are very amazing, and we'll see you next week. Same time, same place.
See you. All right. Cheers all.